So we're continuing on with our discussion of carbonyl chemistry, and we're going to focus today mostly on using H- equivalents as the nucleophile. So we're going to be adding H- to carbonyl compounds. What happens to the tetrahedral intermediate will depend on the carbonyl compound. But we're not going to ever use H- directly as a nucleophile. You may have seen the reagent sodium hydride previously, NaH. This is an ionic compound. It's a salt, and it's pretty insoluble in organic solvents. When you use it in a reaction, it sort of sits at the bottom of the flask as this sort of insoluble chunk, and the surface can react as a base, but it's really, because it's insoluble, it's really not good as a nucleophile. So that's not our hydride delivery reagent of choice. By the way, I guess I should be clear about some things. H-, hydrogen with 2 electrons and a negative charge, is called hydride. Of course, H+ we call proton. And if it's hydrogen radical, we just call that a hydrogen atom or hydrogen radical. So I'm going to refer to hydride delivery reagents, and that means things that will basically deliver H- to organic compounds. So there are a few of these, and some of them have special properties, and there's not really much you can do based on first principles to to remember or understand why these reagents work the way they do. So you may need to memorize some of the nuances. The first is called lithium aluminum hydride. And this is a very reactive reagent. Lithium is the counter ion, aluminum is a metal, and it's bonded to 4 hydrogens. I guess the structure would be sort of tetrahedral. We won't need to worry about that. Now, why is this a hydride delivery reagent? Well, first, notice that aluminum is in the same column of the periodic table as boron, which means if it's bonded to 4 things, it's got to have a negative formal charge. Okay? So right away, the AlH4 molecule is an anion, has extra electron density. So that's clue number 1. Clue number 2 is that if you compare electronegativities, hydrogen is more electronegative than aluminum, which means that much, if not most, of that negative charge has to be out on the hydrogens instead of on the aluminum. Remember, formal charge is really just a way of counting electrons. It doesn't often tell you enough about the actual distribution of electron density in the molecule. So understanding that hydrogen is more electronegative than aluminum gets you to the conclusion that each of these hydrogens has extra electron density and can be nucleophilic. All right? There are other reagents that do this as well. Lithium aluminum hydride, and we'll get onto those in just a second. Lithium aluminum hydride, though, is very reactive. You might imagine that these hydride delivery reagents might be sensitive to solvents and the presence of water. So when you're using lithium aluminum hydride, and we can abbreviate that as this, just write it like that, or some organic chemists get lazy and call it La, right? It's reactive such that you can't use water or protic solvents. In water, what happens is a hydride comes off aluminum, removes a proton from water, makes hydrogen, and then the reaction's so exothermic that you can start a fire or an explosion. So you have to be careful with lithium aluminum hydride. And that has to do with the difference in electronegativity between aluminum and hydrogen. There are some other hydride delivery reagents. One is called sodium borohydride. This is analogous to lithium aluminum hydride, only this is much less reactive. And that has to do with the lower electronegativity difference between boron and hydrogen. So it's not as reactive as lithium aluminum hydride. You can use protic solvents. They're okay because sodium borohydride isn't very basic. And we will see that sodium borohydride reduces some things, but not other things, whereas lithium aluminum hydride will reduce most any carboxylic acid derivative. So those are a few reagents to start with. We'll introduce some others a little bit later on today in the context of some specific applications. So what happens when you expose a ketone or an aldehyde to, let's say, sodium borohydride? And the way you're going to push arrows for that kind of situation is as follows. So for the most part, sodium is the counter ion, which we will ignore. There's evidence that sometimes the counter ion plays an important role, but we're going to ignore that. It won't matter for this class. I'm going to write out sodium borohydride like this. I'm just drawing one of the boron-hydrogen bonds because we're only going to need one to do the chemistry. You may find this to be kind of weird, but remember what I said about sodium hydride not being very soluble. What we're going to do is have the borohydride reagent, the BH4, hand off H- directly to the carbonyl compound. You can think of this as hydrogen leaves with its electrons and then attacks the carbonyl compound. If you think about it that way, though, it should give you a little bit of heartburn because H- should be a terrible leaving group, and I've already told you it's not soluble. So this is more of a direct handoff from one reagent to the other than a group leaves and then comes back in and attacks. The reason that borohydride can hand off that H- is because doing so allows it to become neutral again. Right? After that H- is gone, the borohydride is just borane, BH3, and we won't worry about what happens to that, but that's what's left after the reaction. So I hesitate to draw this because some of you are going to draw the conclusion that I must draw that always, and the answer is, for the most part, when I'm asking you to predict products, we're talking about what happens to the starting material, not really what happens to the reagents. So what happens when you hand off H- to the carbonyl compound? Well, remember, we've been talking about carbonyl compounds as being reactive here because that's where most of the pi star antibonding orbital is. That's the antibonding orbital for the carbon-oxygen pi bond, and the hydrogen gets delivered to that pi star, thereby breaking the pi bond, and electrons move out onto the oxygen. And that gives us the tetrahedral intermediate we discussed last time. And at that point, we ask, are there any good leaving groups on that tetrahedral intermediate? The answer is no. So we're stuck. And it turns out when we're using sodium borohydride, we're probably in some kind of protic solvent. I'm not going to specify what that is. It's often methanol. But if you have solvent that has a proton that can be exchanged in it, it's pretty easy for that negatively charged oxygen to pick up a proton from some other source to give you the alcohol. Okay? So that follows the pattern we've been learning. And you don't need to memorize that. If you understand what borohydride does as a reagent, and you understand carbonyl reactivity, you don't need to memorize that aldehydes react with sodium borohydride to give you a primary alcohol. All of that just follows automatically from your understanding of the chemistry. All right, questions so far? Yeah?
Why does it hand off to that carbon, not the other one?
Why does it hand off to this carbon instead of this one? Okay, the carbon on the left is not the electrophilic portion of this molecule. It's a sp3 hybridized carbon that has bonds to hydrogens and carbons. There's no good leaving group there, and there's also no low energy anti-bonding orbital sort of here. So yeah, that's the reactive portion of the molecule. One of the key skills to get in organic chemistry is focusing in on the relevant details. That's why I talk about HOMO and LUMO, because it helps you focus in on the reactive part of the molecule, and then you can ignore other things. So yeah, that's why I didn't even say anything about this methyl group, because it's not going to be involved in this reaction. Stay tuned though, because we will be doing stuff with that methyl group in the future, just not now. All right, what else? Yeah?
Should we pay attention to what happens to the ionized solvent after it's deprotonated?
Should you pay attention to what happens to the ionized solvent after it's deprotonated? That would be the methoxide. No. Though you wouldn't be surprised if you did this reaction to discover that at the end, if you added water, the reaction might get a little bit hot as you do the acid-base chemistry. I don't know. No, don't worry about it. It's the kind of thing, like I was saying last time, once you get to a tetrahedral intermediate and you're stuck, often there is a workup step where you dump water and perhaps some buffer into the reaction vessel, and that protonates what needs protonating. So, yeah. What else? Did I see another hand? No? Okay. We can do this with ketones as well. There's sort of no surprises here. Here is a particular ketone. This time, just for fun, let's use lithium aluminum hydride. That's sort of bringing the big guns for a problem that doesn't require it. You could use sodium borohydride, and frankly, if you can get away with sodium borohydride, you do, because it's so much easier to use than lithium aluminum hydride. For your purposes, though, you can use them on aldehydes and ketones interchangeably. This is going to deliver, again, a hydride equivalent to the carbonyl carbon, to the pi star. Lithium is the counter ion. There's some evidence that that lithium is associated with this carbonyl oxygen, but we won't worry about that. Aluminum hands off H minus to the pi star of the carbonyl compound at the carbon. We break the pi bond. We get a tetrahedral intermediate. Sorry, there we go. Now, here's an important point, because if you look at what we have done, we turned an sp2 hybridized carbon into an sp3 hybridized carbon, and this one is now bonded to 4 different things. So we just made a stereocenter, right? And you cannot, this is sort of a fundamental principle, you cannot get chirality out of nothing. If you make a stereocenter in a molecule that you make from non-chiral starting materials and non-chiral reagents, you must get a 1-to-1 mixture of both stereochemistries, okay? So lithium aluminum hydride is not a chiral reagent. This starting ketone is not chiral. So we have to get both stereochemistries. What this means is that aluminum hydride can, and the reason this happens is because aluminum hydride can deliver the hydride reagent from above or from below. Above, by above, I mean above the plane of the page, so from this direction, or from back beneath the plane of the page. Okay, so those are both, those two compounds are enantiomers of each other. We get both of them. And of course, I haven't shown you the after the fact aqueous workup step where we would remove a proton from water to get the alcohol. So I'm not going to draw that because proton transfer reactions are very easy. You've already seen it there. So I'm just going to show you the final products. All right. So we need, go ahead.
On test, would you want us to put like racemic deal, or do you want to draw both?
Right, so on test, what do you do to show that you get both starting materials? Well, I'm sorry, both enantiomers. There's multiple ways you can do this, so you have to be careful about what you're communicating. It's always okay to draw both enantiomers, okay? It's also okay to draw a molecule like this without any dashes or wedges. That communicates that you get both enantiomers because you haven't specified stereochemistry. In this drawing, I can't tell whether it's R or S, so I have to assume you mean both, okay? Now, what, is that blasphemy? I just gave you permission to be lazy, right? You can draw one thing instead of two. Yes, but be careful. I have to warn you that if you're in a molecule that already has a stereocenter, I'm trying to make up something here, and it's not going to go particularly well because this is going to be a dumb example. All right, suppose you reduce this molecule with sodium borohydride, and you suppose you draw the product like this. What's wrong with that, other than it's lazy? Go ahead.
You already have the stereochemistry in your reactants. You got to show the products too.
Right, I had a stereocenter, oops, I had one. I had a stereocenter here, and that stereocenter is not involved in the reaction. If I draw it without any dashes or wedges there, I communicate that I think this reaction not only gave me one-to-one stereochemistry here, not only gave me both stereochemical configurations here, but also gave me both stereochemical configurations there. All right, so it's laziness, but principled laziness, right? You can't be lazy with stereocenters that are shown to you with a specific configuration and that are not involved in the reaction. Those have to stay the same, okay? So that's just sort of a warning. A final option, which some people like, I don't know that your text uses it, but I've seen people use this abbreviation, is to draw one of the two stereoisomers, one of the two enantiomers, and in parentheses, sorry, I don't really like how I drew that, draw one of the two stereoisomers, and then in parentheses put a plus or minus. That harkens back to the fact that you can characterize chiral compounds by how they rotate, plane polarized light, optical rotation. And one stereoisomer will rotate in the clockwise direction, and one will rotate in the counterclockwise direction. That's plus degrees and minus degrees, for example. And so that plus or minus indicates you've got both stereochemical configurations. Any of those three options are fine. But again, beware not showing any stereochemistry. You may inadvertently communicate that which you ought not communicate. That was too fancy. All right. Other questions? Yeah.
What about DL?
DL. DL. Oh, right. Like, Sometimes sometimes you will indicate a racemic mixture of enantiomers with a DL in front. I'm not sure how you would do that there, but yeah. I'll give you a little hint though, guys. Most of my, friends, guys is too gender specific, isn't it? So my wife Amber and I are interested in studying the scriptures. We've been learning a lot of stuff, and what's sort of bothered Amber recently is how sort of male-centric the scriptures are. The pronouns are all he. When it means mankind, it says man. And anyway, that's all. I don't want to start anything. Because you can't, we don't want to be accused of presentism where we try to impose upon the past the social mores of today. Nevertheless, I feel like inclusive language is important. So I will maybe sometimes use not to refer to males, but people in general, but I will call you all friends instead. Is that okay? Okay. Because in this classroom, we value male and female perspectives equally, right? All right. I just lost the train of thought. This will happen a lot. I'm easily distracted. Oh, yes, I will give you a hint. My exams are generally multiple choice, and so you won't necessarily be drawing things on exams. Nevertheless, I am perfectly capable of drawing wrong answers and deceiving you into selecting them, right? You can bet that was going to be one of the answers, right? I'll tell you more about exams as it goes on. You may be relieved to hear that it was multiple choice. You shouldn't be. The scores on my multiple choice exams are about the same as my free response exams previously were. They're just easier to grade, which is better for me. And they are easier for you to get immediate feedback about how you did, which is maybe better for you. Instant response is sometimes good, sometimes not. The other thing it allows me to do is if I've made a mistake or want to give partial credit for some answers, I can do so evenly across the class, not just for those intrepid souls who come up to my office. So anyway, we'll talk more about that as the exam gets closer. Sorry. Let's talk about nature, though, because nature's biomolecules are chiral, and so nature is capable of delivering hydrides in a manner that selectively results in one enantiomer over the other. We call that enantioselective. I told you that lithium aluminum hydride is too reactive to be in water. Well, aqueous solvent is really much of what we have in nature. And so you need a hydride delivery reagent that can withstand water. And so nature's reducing reagent is called, here we go, nicotinamide adenine dinucleotide. And if you know the secret code words and about biostructures, you can draw that, and I'll draw it for you. But that's a mouthful, and so people call this NADH. Have you heard of that molecule before? Maybe some cell bio, something like that. Okay, so we're going to draw that, but this is a reducing reagent. So I'm going to draw the business end of the molecule first. This is the nicotinamide portion. And if you were drawing a mechanism using this molecule, this is the only portion you would need to draw. Okay. Let's see, shall we? Yeah, why not? This portion of the molecule that we get, and don't get excited, this is not just a methyl group, there's like a big whole thing down here. This portion we get from the vitamin niacin, which is vitamin B3. The precursor is, let me get that right maybe, June? Yeah, that's niacin. So when you see on your marshmallow mateys in the morning that it's fortified with niacin, it's got some of that in it. And why? Because you need to be able to make NADH. Okay, next is the nucleotide part, dinucleotide part. So this nitrogen on the here on the sort of niacin ring is attached to the ribose sugar, which is a 4-membered ring, 2 oxygens, 4-membered, that's 5, count. 5-membered ring. Nobody, well, some of you have watched Sesame Street in your life, that's good. The count. Yeah, so here's the ribose ring. There's a phosphate there attached to another phosphate there. This is called a phosphoanhydride. And then that phosphate is itself attached to another ribose ring. And that ribose ring is attached to the base adenine. So let me reassure you as we're having fun drawing that the question that I always get, do I need to memorize the structure of NADH? No. Well, if I don't need to memorize it, why should I care? Because this stuff keeps you alive. All right. So this is the reducing agent part of the molecule. This portion is really about binding the right part of the enzyme. Okay. That does the reaction. So how does this reagent work? Let's focus in on the niacin ring. I guess before we go on, any questions you want to ask about that? Okay. Yeah.
Why did you include a stereochemistry on the 2 hydrogens? It's not a stereochemistry.
Right. Why did I include stereochemistry on those 2 hydrogens? Because it's not a stereo center. To communicate geometry, to reinforce that that's an sp3 hybridized carbon with tetrahedral geometry. Because it's those hydrogens that are involved in the reduction. Okay. So remember, I told you lithium aluminum hydride will deliver a hydride to a carbonyl compound. So will NADH. All right. So maybe we can do this with what we've already drawn. Here is, I'm going to draw the alpha keto acid pyruvate. This is the end point of glycolysis, metabolism glycolysis. And of course, if you're undergoing aerobic respiration, you can shunt pyruvate into the citric acid cycle and get a ton more ATP out of it. But under sort of anaerobic conditions, pyruvate accumulates and NADH can reduce it. What happens is NADH, I'm going to put the lone pair there, sorry, delivers the hydride to the carbonyl compound. And does so in an enantioselective way because of the enzyme. So it delivers the hydride from above. If it's okay with you, I'm not going to draw the negatively charged tetrahedral intermediate. That's going to be protonated in the next step. Everybody good with that? We're good with not drawing, even though that happens. And then what's left over here, I'm going to use R for all of this stuff. Lazy, right? I'm going to redraw the nicotinamide ring. Okay, what if I just hand off H minus, what should I have left on this carbon? A plus, right? But understand that actually that positive charge is delocalized. I can draw a resonance structure in which I move these electrons here and these here, and then I have a positive formal charge on the nitrogen. And actually, this resonance structure here on the bottom is probably a better one because everything's got a full octet of electrons. And in fact, some people will actually draw the mechanism like this. They'll have these lone pairs kick down and this pi bond move over as the reason for why hydride can leave. Okay? So there's some stuff that's unfamiliar here. The unfamiliar stuff includes what we just barely learned, which is how can hydride leave the delivery reagent? And remember, it's a direct handoff. So this arrow that goes from this hydrogen-carbon bond takes these electrons and takes the hydrogen and attacks the pi star at the carbonyl carbon. That arrow is exactly analogous to what we did before with lithium aluminum hydride. The other new stuff is what happens to the ring, and that's less essential. The reason you can get rid of the hydride is that this portion where the hydride is gone is actually not that different in stability from this. The reason for that, yes, you have given up a carbon-hydrogen bond, but you've also made this six-membered ring fully conjugated. Before, it was a six-membered ring where one of the atoms was sp3 hybridized. Here now the ring is fully conjugated. You learned about conjugation in 351 for the most part, right? If you took it last semester, did you do conjugation in dienes? We haven't done aromaticity yet, but the same principle applies. Aromaticity is conjugation in a ring if the ring is the right size and you have the right number of electrons. We'll get to that later. But by establishing conjugation, you pay for much of the loss of that hydride. Okay? All right, so that's nature's hydride delivery reagent. It's used all over. You'll hear a couple of things. Sometimes people, biochemists will write reactions with, they'll say, oh, we take pyruvate. They'll say, oh, we take pyruvate and then we use NADH, and they'll often put a comma and then a proton. Then they will show a little bendy arrow like this to indicate that the enzyme takes NADH and a proton and spits out NAD+. What is NAD+? That's this oxidized form of NADH. What the heck is with this proton here? There are no free protons in biology, right? It's not like we have H pluses following around. It's all H3O plus, right? So this is just pure laziness, but I can't complain too much because I was lazy too. That's that proton that protonates the tetrahedral intermediate. Okay? So now when you get to biochem and you see all this stuff about NADH, comma, H+, what the heck is that? They're just trying to pretend like they're balancing equations and keep track of the fact that you need to protonate a tetrahedral intermediate. Yeah?
So when you protonate the tetrahedral intermediate, why does that not affect the reagents that are like really affected by protic solvents?
So when you protonate the tetrahedral intermediate, why doesn't that affect the reagents that are affected by protic solvents? You're exactly right. I think the situation you're referring to is back here. If I got the tetrahedral intermediate and then in a second step, I add water to protonate that, isn't that also going to mess with the lithium aluminum hydride? Yes. So you have to do it slowly and on ice and under an inert atmosphere to prevent problems. Yep, but you don't care because the reaction's done. In the case of lithium aluminum hydride, in the case of biology, this reagent in its NADH and NAD plus are perfectly stable in water, so it doesn't matter. Other questions? I saw another hand. Did I miss something? Yeah.
If this reaction occurs in a protic solvent, why is the oxygen with the negative charge not protonated?
If this reaction occurs in a protic solvent, why is this negatively charged oxygen not protonated? This is a carboxylic acid. I'm showing you the form that would exist at physiological pH of 7. We'll return to this in maybe a week or so. The pKa of carboxylic acids is in general in the range of 4 to 5. This one might be a little bit lower. If the pH is higher than the pKa of an acid, the acid loses its proton. So you'll see that most carboxylic acids are negatively charged in biological contexts. It's the conjugate base. Let's see, another hand, yeah.
So in the book it talks about how there's an enzyme that's involved in this reaction. Are we going to worry about that at all?
So are you going to need to worry about the enzyme? There will be times where we talk about what the active site is and how it works. For this particular case, no. I will say that the enzyme that does this, the molecule, by the way, that's made is called lactate. And this is associated with the tired feeling of muscles, especially under anaerobic type exercise conditions. The enzyme that does this, I think, is called lactate dehydrogenase. If you see enzymes in biochemistry with the name dehydrogenase, that almost always means that they are doing a reduction or oxidation reaction. The maddening thing is that this reaction and the enzyme is named for the backwards reaction. So just like we reduced pyruvate to lactate, we can use NADH to do the backwards reaction where we oxidize lactate to pyruvate. Notice the difference between lactate and pyruvate. It lacks this hydrogen here and that hydrogen there. That's why the reaction is catalyzed by a dehydrogenase. Okay, so this is introducing a little bit of biochemical nomenclature that's not going to matter for our class, but you'll see it in the future, and I want you to make a connection with stuff you already know. Yeah?
In the pyruvate, why is the hydride only added to the number 2 carbon?
Right, why is pyruvate only added here and not here? The answer is that negatively charged carboxylic acids are not electrophilic because they have that extra electron density. That's going to repel a nucleophile that comes close. Yeah.
And then one more question.
Yeah.
Why is the in the lactate then? Why is the oxygen on the end not, I guess, hydrated?
Right. Oh, okay. So why don't we do this? You could, only at pH 7, the form that exists is the conjugate base. We'll talk about that. You may have learned it in chapter 2, but we'll review it. You can use the good old Henderson-Hasselbalch equation to tell whether in aqueous buffered solvent a proton should be there or not. Yeah. Okay. Others? Yeah.
So it'll only ever take the H that's on top of the NADH molecule?
Will it only ever take the H that's on top or the bottom? That's going to depend on where the enzyme holds the pyruvate or whatever you're reducing and where the enzyme holds the reducing agent. I think there's evidence that one is preferred over the other. I don't think it's consistent from enzyme to enzyme.
So we don't need to worry about
Yeah. Somebody else? No? Yeah.
So you said this is stereo-specific, right?
Yep.
Why is it that it has the hydrogen on top?
Okay. So I think maybe the word to use is enantioselective. Stereospecific is a term we use for reactions where the stereochemical outcome has to be a certain way. Stereoselective is where we use a term where the situation prefers one over the other. So you can imagine this. Suppose, okay, your hand is chiral, right? Enzymes are chiral. We're going to imagine your hand is the enzyme. So reach your hand under the page and sort of hold pyruvate there. And your hand is blocking the bottom face of pyruvate. The top face is accessible, and that's where the hydride gets added. That's sort of hand wavy, but that's effectively what happens. The chiral enzyme holds the pyruvate and the NADH in a specific orientation such that only one face is accessible. Okay, yeah?
And since the enzymes are pretty specific in how they fit with the things they're catalyzing, aren't they usually designed such that they hold the pyruvate and the NADH at certain points so they can combine at certain points too?
So I'm not sure I understand the question, but so can you try again? Because I'm a little dense, and they are held in a specific orientation that prefers addition from above in the way I've shown you, but that wasn't your question.
That was what I was asking.
Okay, yeah. Yep, that's the role of the enzyme. Cool, right? So now we need to talk about we're going to jump back from biology and start thinking about what if we wanted to use some of these reagents to reduce carboxylic acid derivatives. These are molecules that have a carbonyl, but then that carbonyl carbon is also bonded to something that could be a leaving group. We'll use Z instead of Y, where Z is some kind of potential leaving group. Abbreviations of abbreviations, I'm sorry. So let's start most simply with an acid chloride. And let's think about using lithium aluminum hydride on the acid chloride and think about what would happen. So as we did above with the with the aldehyde or the ketone, except now I'm making stuff up, we're going to have aluminum hydride deliver H- to the carbonyl carbon. We're going to get our familiar tetrahedral intermediate. But unlike the ketone and the aldehyde, we now have a decent leaving group on the carbonyl carbon. So, like we did last time, the thing that can happen is the negative charge on the oxygen can kick down and kick off Cl-. And we know that that's a reasonable step because it's more stable to have a negative charge on on chlorine than it is on oxygen. You can tell that because the conjugate acid of the negatively charged oxygen is an alcohol, pKa 16. The conjugate acid of chloride ion is HCl, pKa like -9. So what I'm telling you is this reaction in the forward direction is favorable. All right? Well, that's fine, but I just barely told you that lithium aluminum hydride can reduce aldehydes to alcohols. And so what will happen next is another molecule of lithium aluminum hydride will attack the aldehyde, and you will get the alcohol. I'll show you the negatively charged tetrahedral intermediate, and then in a second step, you're going to add water to quench the reaction. When you do that, you will remove a proton from water and thereby generate your alcohol. Okay? So lithium aluminum hydride will take the acid chloride and go all the way to the alcohol instead of stopping at the aldehyde. Now, at this stage, I usually get a question about, well, what if I only added 1 mole of lithium aluminum hydride per 1 mole of acid chloride? And the answer is complicated. maybe I'll just say it doesn't work very well because the aldehyde is reactive, and as soon as you start to form some aldehyde, the remaining lithium aluminum hydride will then have to choose between acid chloride and aldehyde, and then you're going to get a mixture of products. The other secret is a mechanism I haven't, details that I haven't shown you would indicate that one molecule of lithium aluminum hydride can actually reduce 4 different molecules instead of just one. That's a detail you can just in one ear and out the other. But for to be simple, it just doesn't work to try one equivalent. Lithium aluminum hydride is too reactive. It takes the acid chloride all the way down to the alcohol. This happens with esters as well. So the ester is like this, and via the same mechanism, if you use lithium aluminum hydride with the ester, you will reduce the ester to the alcohol, and these are the 2 hydrides that you delivered. All right. I'm not going to draw that mechanism. The tetrahedral intermediate, maybe I'll draw briefly for you, is this one. And hopefully you can see that it's reasonable for a negatively charged oxygen to kick off another negatively charged oxygen. At that point, it's exactly the same mechanism. You make an aldehyde and you reduce it again. Okay. One important detail is that sodium borohydride doesn't generally reduce esters or acid chlorides. We can use it selectively for ketones and aldehydes, but not for esters. Why? I suppose it's not reactive enough, but that's more of telling you what happens than why. So that's a detail you'll have to memorize. You're not going to use sodium borohydride to try to reduce an ester. And if you see some synthetic scheme later on where somebody is using sodium borohydride in the presence of a molecule that has both a ketone and an ester, then you'll know what's going on. Let me maybe be clear about that. Suppose you have a molecule like this. You could use sodium borohydride to reduce the ketone to an alcohol without touching the ester. ET is not the extraterrestrial, it is instead an ethyl group. Okay. Question so far? Yeah. Oh, we got 2. Sorry, you were both in the direct line. So let's start back there first and then in the front.
If you were to use the lithium, would you ever reduce
Yes, if you were to use lithium aluminum hydride on this same starting material, you would do both the ketone and the ester. So this is sort of the finesse approach, and this is the without any finesse. It's you bring in the hammer. Yeah, go ahead.
We suggest that because you said that
Sodium borohydride isn't going to reduce esters. I'm not sure with acid chlorides, but we'll pretend like it's that way. There are other carboxylic acid derivatives we need to talk about that we haven't, but sodium borohydride doesn't work on those either. Okay, guys, I estimate that we're maybe half a lecture behind already. So we're going to be flexible in terms of where we get to.